Hello, this is chapter 11.2, and in this chapter we're going to discuss the synthetic methods towards alkyl halides and how to make alcohols better leaving groups. Here's the video breakdown. In video 1 of 2 we'll discuss some new reagents that can be used to make alkyl halides from alcohols, and in the second video we're going to discuss how to make alcohols better leaving groups, and this is by derivatization of the alcohol. There are 3 possible synthetic methods for making alkyl halides from alcohols. In the first instance, this is marked by the yellow pool ball. We're treating the R prime group as a methylene group, that's CH2, thus making this a primary alcohol substrate. You may recall from chapter 7 that the reaction of a hydrohalic acid, such as hydroiodoic or hydrobromic acid, will afford the primary alkyl halide. If reaction route 1 is attempted with any other alcohol substrate, such as a secondary or tertiary substrate, then this could lead to carbocation rearrangement or certainly undesired reaction products. The second route, that is marked by the blue pool ball, is for making an alkyl bromide or a bromoalkane. This involves the SN2 reaction of the primary or secondary alcohol with phosphorus tribromide, and this is great because there are no rearrangements. The last route, as marked by the red pool ball, gives access to alkyl chlorides or chloroalkanes. This route involves the use of thionyl chloride and also works through an SN2 reaction mechanism. So again, this route will work best with primary and secondary alcohol substrates. Let's look at each reaction in turn. First, we will start with the reaction of primary alcohols with hydrohalic acids to yield alkyl iodides and alkyl bromides, aka iodoalkanes and bromoalkanes. Initially there is an acid-base reaction, so the alcohol group is protonated in this case by hydrobromic acid under reflux conditions. This hydrobromic acid and hydroiodic acid are both very strong acids, and these contain very weak conjugate bases, and this is shown by their pKa values on the bottom left of this slide. Now, hydrochloric acid can be made to work for primary alcohols by this route, but this will need a catalyst, and this we'll discuss on the next slide. Bromide and iodide are decent enough nucleophiles to attack the primary carbon of the protonated substrate, as this is relatively unhindered, and this will cause the water molecule to leave SN2 fashion and give access in this case to 1-bromopropane. Now let's take a look at the use of hydrochloric acid with an appropriate catalyst. Typically acids will protonate the alcohol group, making it a good leaving group. However, other strong Lewis acids can be used instead of hydrohalic acids. Now, in the case of the chloride ion, this is a weaker nucleophile than either the bromide or iodide ions, so hydrogen chloride does not react with primary or secondary alcohols unless there is some zinc chloride or a similar Lewis acid is added to the reaction mixture as well. Zinc chloride, a good Lewis acid, forms a complex with the alcohol through association with an unshared pair of electrons on the oxygen atom. And what this does is it enhances the alcohol's leaving group potential such that the chloride can now behave as a nucleophile and displace it as a leaving group. Let's summarize this on the next slide. None of the reactions given on this slide work, and the reasons provided are given. Please pause the slide and read through these. Carry on once you're ready. The slide advances after 5 seconds. Remember, if you have a secondary substrate, then it's probably best to use phosphorus tribromide. This will also work, of course, for a primary substrate. The use of a hydrohalic acid will probably lead to the side reactions we discussed if you try to do this with a secondary substrate. So, how does this reaction yield an alkyl bromide or a bromoalkane? Let's take a look. Here is the overview of the reaction. So 3 equivalents of alcohol are required for reasons that we'll discuss on the next slide. Please note that the reaction will proceed via SN2, and so this will lead to an inversion of stereochemistry. Let's now discuss the mechanism. This reaction proceeds in 2 steps, and you can think of these 2 steps as being activation, which is improving the leaving group ability of the alcohol, and then the subsequent substitution. Now, in the activation step, the alcohol is being converted into a better leaving group by forming a bond to phosphorus. Oxygen-phosphorus bonds are very strong. The next thing that will happen is that the bromide that's displaced from the phosphorus, this is essentially the nucleophilic substitution part, this will come in and kick out that leaving group. Now this happens 2 times over, and there is always an inversion of stereochemistry. It is not essential for you to know the mechanism of this reaction. Here is a summary slide for the bromoalkane or alkyl bromide synthesis. So take the time to pause the video and read through this slide. The slide will advance to the next one after 5 seconds. The final route is now discussed, and this involves the use of thionyl chloride with primary and secondary alcohol substrates to yield chloroalkanes or alkyl chlorides. The mechanism of this reaction is not essential for this course. If the same substrate is used as in the previous reaction, there are 2 possible stereochemical outcomes that you should be familiar with. Thionyl chloride is necessary to provide the source of chloride ions in this reaction. However, when used with pyridine alone, the reaction does proceed via SN2 and leads to the standard stereochemical inversion as seen here. However, if pyridine and a 1,4-dioxane solvent is used, the stereochemistry of the reaction is retained. That means that we end up with a double substitution, and so we have an R stereocenter to begin with and an R stereocenter to end with. Let's look at a summary slide for this reaction now. Here is a summary slide for chloroalkane synthesis. Please pause the video and take the time to read through it. This slide advances after 5 seconds. This concludes part A. The sulfonate esters are used as leaving groups as they help to activate alcohols. Here are some of the reagents, their free leaving groups, the pKa of their conjugate acids, their abbreviations, and the names of those sulfonate esters. The first reagent is known as mesyl chloride, and this forms the leaving group shown to the right when it is reacted with an alcohol. When you look at the pKa of the conjugate acid for this leaving group, this is methane sulfonic acid. Its pKa is on par with a protonated alcohol group. So these reagents provide an alternative reaction route to the use of a strong acid. And one has to be mindful that using a strong acid on an organic reagent is often like taking a sledgehammer to a nut. In other words, it's really not a good idea. If you remember from chapter 6 that a low pKa provides some indication about the leaving group ability, then one can appreciate that this mesylate group is a weak stabilized base. And the stabilization, of course, comes from our friend resonance. Now, what if we want an even better leaving group? If that is a requirement, then the tozar group is about 10 times more acidic than the mesyl group, and this is another option. So the tozar leaving group of a para-toluene sulfonate ester is even more stabilized as additional resonance stabilization comes from that benzene ring that's attached. Now the last group is a super leaving group. These are known as triflates. Now whilst it might seem like a good idea to use this one, This leaving group is apt to leave of its own accord, so for certain substrates this could be an issue, especially if rearrangements are a possibility. Let's now have a look at how a sulfonate ester is made from an alcohol. The alcohol substrate is reacted, in this case, with mesyl chloride, but it's the same process for forming any of the other sulfonate esters. Note that the oxygen atoms react with sulfur and nothing at this point happens to the stereochemistry of that chiral center. This reaction proceeds with retention. Afterwards, a suitable nucleophile can be used for an SN2 reaction under the usual conditions, a low temperature and a polar aprotic solvent. At this point, the reaction will proceed with inversion at that chiral center, and the mesyl leaving group leaves because of the resonance stabilization.
This concludes part C.